Okay, marhaba. In this session, we want to talk about objects in mathematics called matrices. Matrices is the plural of a matrix. So what is a matrix? Let us define it. So simply, and suppose m and n are positive integers, then we say an m by n matrix. Okay, so this is the main word of today, is an array, okay, or is a rectangular array. So it's a two-dimensional array of real numbers. Okay, so it could be of complex numbers, but in this course we restrict ourselves to real numbers. So it's a rectangular array of real numbers, in which this array consists of, so with m rows and n columns. Okay, so you just imagine that we have real numbers arranged in a table or in an array with m rows and n columns. So let's have some example. And by the way, we call this m by n. So we call this the dimension of the array, and the dimension of the matrix. Okay, so let's have an example of a matrix. For example, look at this matrix. We use these square big brackets to denote matrices, and here we have, in the first row we have the number 1 and the number 2, and in the second row we have the number 5 and the number 7. Okay, so this is called a 2 by 2 matrix. Okay, so m is the number, the first number is the number of rows, and so this is, see, row 1, this is the first row, and this is row 2. So this number 2 for the number of rows, and this number 2 is for the number of columns. So this is column 1 and this is column 2. Okay, another example is, say, 1, 4, 6, 2, negative 7, 24. Okay, so what is this? This is a matrix of what dimension? Okay, 1, 2, 3 rows, so it's a 3 by 1, 2 columns. So this is a 3 by 2 a matrix. Now another example is this example. For example, we have say 4, 6, and 8. So here we have 1 row and 3 columns. So this is 1 by 3 matrix. A matrix composed from 1 row and 3 columns. This is called a row matrix. Now, similarly, we have, say, 1, 2, 3, and negative 7. Okay, so this is another matrix. This is called the column matrix, and it's composed of 1, 2, 3, 4 rows and 1 column. Okay, so these are like examples, several examples of matrices. Now, let me tell you that when m is equal to n, that is, the number of rows is equal to the number of columns, we call it a square matrix. Okay, so when you see the term square matrix, it means the number of columns is equal to the number of rows. Like this one, it's a 2 by 2 matrix. This is a square matrix. Okay. Now, we want now to introduce the notation used to represent matrices. Okay, so suppose we have a matrix A. We have a matrix A of dimension m by n, which means it has m rows and n columns again. So this is for rows. The first number is for rows and the second number is for columns by convention. Okay, now how do we represent this A? Remember that A, what is A? It's a rectangular array of m rows. So we imagine we have an array. So I'm introducing the general notation. And suppose we call we use the small letter a to represent the entries. We call the elements inside the matrix the entries of the matrix. Now look at the first row. We will represent the first element of the first row by A11, and then A12, and then A13, and so on. Okay, so let me just remove this. Okay, and so on until what is the last element here? It's A1. So the first index represents the row number, so we are in row number 1, and the second index represents the column. So this is column 1, column 2, column 3, and what is the last column? We have n columns, and this should be n. Okay. Now similarly, we write the elements or the entries of the second row. Now because it's the second row, the first index should be 2. So this is the second, but the first column. Okay, so this is A22, and this is A in the second row and third column, and so on until in the second row and nth column. Okay, so this is, for example, the third column. Okay. Now we keep doing this, okay, until say we go to the ith row. So this will be AI1. So this is the ith row. And this will be AI2 because it's in the ith row and the second column. And this is A, okay. Let me keep doing this until the jth column. So we will be in the entry Aij. And the last entry will be AIN. Okay, so what is this? So if there's a column here, this column is the jth column. Okay, and then we keep writing all the rows until what? Until we exhaust all of them. But how many rows we have? We have m rows. So the last one will have index m and then 1 for the first element in the mth row, right? This is the last row, which is the mth row. Because look, we started with a matrix which has m rows and n columns. And this will be AM2, and so on. This will be AMJ, so mth column and mth row and jth column, and the last one will be in the mth row and the nth column. So this will be AMN. Then we close our matrix. Okay, so this will be the general notation, and all this like complicated notation will be represented by this shortcut. We will use a square and then write Aij and then square it. So when you see this small square brackets with Aij, we mean all of this. Okay, so we mean all of this. All of this notation is represented by this compact notation. Okay, what is Aij? This is the entry which lies at the intersection between the ith row and the jth column. Okay, so remember, first index represents the row number, and the second number j represents the column number. Okay, so this is our Aij in general. So Aij lies in the ith row and in the jth column. Okay? So this will be our general representation of a matrix, and we need this general notation for matrices to prove theorems about matrices. Okay, this is a very important notation. Okay. Now we want to define some relation, okay, on matrices. We want to define when two matrices are equal. When we will consider two matrices are equal. So suppose we have a matrix A whose entries are denoted by Aij, and another matrix B whose entries are denoted by Bij. So what is Bij? It is the entry which lies in the ith row and the jth column of the matrix B. Then suppose we are given these two, given A and B, we consider, okay, we declare them equal. We declare A is equal to B if and only if two conditions are satisfied. One, A and B have the same dimension. And by same dimension we mean they have the same number of rows and the same number of columns. And second, the corresponding entries are equal. Okay, so two, the entry in the ith row and the jth column in the matrix A is equal to the corresponding entry in B, which is Bij. So to the entry in the ith row and jth column in B. So these entries are equal for all what? I, but I ranges what? From 1 to m, say both have same dimension m by n. So we have m rows and n columns. And j represent the number of columns, and so columns ranges from 1 up to n, because we have n columns and we have m rows. Okay, again, this the first number for rows, the second number for columns. Okay, so this is how we define equality for matrices. Two matrices are equal if they have the same dimension and the corresponding entries are equal. Okay, so for example, if you know the matrix A is 2, 4, 6, 7, 1, -6. So this is the matrix A, and you know that the matrix A is equal to the matrix B, 2, 4, Z, A, 1, and -6. Since they are equal, then they have the same dimension. They should have the same dimension, yes, which is 2 by 3, 2 rows and 3 columns, and here as well, 2 rows and 3 columns. And moreover, that the entries have to be equal. So this entry is equal to this entry, 4 is equal to 4, 6 is equal to this entry, and so from here we know that Z must be 6, and 7 is equal to A. So from here we know that A is equal to 7, 1 is equal to 1, and -6 is equal to -6. Okay? So we know, since they are equal, we managed to find the values of Z and A. Okay, another remark about equality is that now the matrix 2, -3, square root of 2, 22. Okay, this matrix is not equal to this matrix 2, -3, 4, and 22. Why these two matrices are not equal? Okay, although they have the same dimension, which is 2 by 2, 2 rows by 2 columns, but there's a problem that this entry, what is this entry? This is A21, right? If we call this matrix A and this matrix B, and this entry is B21 as well. In the second row and first column, they are not equal. Okay, this entry is not equal to this entry. All the others are equal, but for two matrices to be equal, all corresponding entries have to be equal. So this means, since we found one entry where the matrices which are one entry in A which is not equal to the corresponding entry in B, so it's not equal, then this means that the whole matrix A is not equal to the matrix B in this example. Okay? Now, what we will do next is we will define what is called matrix addition. So we want to define an operation on matrices. So how do we add matrices? Now, to add matrices, we have to have the following setting: a matrix A, whose entries are denoted by Aij, and it is of dimension m by n; another matrix B, whose entries are denoted by Bij, and also it has the same dimension. Okay, so to add matrices, we have to have the same dimension. Okay, once we have this input, this data, then we can define the addition. So say we define the matrix C, where C is the matrix A plus the matrix B, and let's denote the entries of C by Cij. Now how do we know a matrix? By knowing its entries. So it remains to define what is the entry Cij, where, so what is the entry Cij? It's the entry in the sum which lies in the ith row and jth column. So where Cij is equal to Aij plus Bij. So this is the definition of addition of matrices. What does it say? That when you add two matrices, you get a new matrix whose ith jth entry is equal to the summation of the corresponding entries in A and B. Okay, so notice that all these entries lie in the ith row and jth column. So all what I'm trying to say that if we have this is the matrix A, we have say 1, 2, 3, 4, okay, 6 and 4. So this is the matrix A. It's 2 by 3 matrix. Let's add it with another matrix, call it B, and it's equal to 7, 1, 1, 2, 2, 2. Okay, and this matrix is equal to the matrix C. Okay, where C, so notice that this is a 2 by 3 matrix. It has 2 rows, 3 columns, and this is a 2 by 3 matrix. And to obtain C, all what we want to do is add the corresponding entries. So we add, what is this entry? This is A11, and this entry is B11. 7 plus 1 is 8, so C11 is equal to A11 plus B11, which is 8. And so on. Now we add this entry plus its corresponding entry. 2 plus 1 is 3 to get this entry, and then 6 plus 1 is 7, 3 plus 2 is 5, and 4 plus 2 is 6, and 4 plus 2 is 6. Okay, so this is the matrix C, where C is the summation of the two matrices A plus B. Okay, and okay, notice that if we have this matrix 1, 2, 4, 7 plus 1, 7, then this summation of matrices is undefined. Why? Because we defined addition for matrices to be of the same dimension, but this dimension is a 2 by 2 matrix. However, this is a 2 by 1 matrix, so we can't perform the addition operation on these two matrices. And finally, let us denote the m by n 0 matrix by bold 0. So say for simplicity 3 by 3. What is the 0 matrix? It's 3 by 3. It's the matrix which consists of 3 rows, 3 columns, and all the entries are zeros. Okay, so, and if I say 0, 2 by 1, then okay, then there's, so for every dimension there's a 0 matrix. So 0, 2 by 1, it is this one. It has 2 rows and 1 column, and all the entries are zeros. Okay, and notice that if A is a matrix of dimension m by n plus the 0 matrix of m by n, then what is the result of adding these two matrices? We see that we get A here. Okay, because we are adding a real number with 0 to get the same real number. Okay, so for example, if we have 7, 4 plus the 0 matrix of dimension 2 by 1, it will be this matrix. Now, how do we add these two matrices? 7 plus 0 is 7 and 4 plus 0 is 4. So we get the same matrix whenever we add the 0 matrix to it.